Hello, today's chapter is chapter 9. It's on statics and torques. We'll be talking about center of mass and equilibrium and all kinds of cool stuff. So you can have static equilibrium and dynamic equilibrium. In static equilibrium, everything's at rest. So all the forces are balancing each other. Any forces pulling you down are balanced by forces pulling up. And the net force acting on the object will be zero, so nothing's going to move. An object in dynamic equilibrium is moving with a constant speed, and the net forces acting on it are zero. So you will move at a constant rate if you're in dynamic equilibrium. You will not be accelerating. So let's look at center of mass. Some of you may know something about this. The center of mass is a place on an object where if you pretend that all of the mass is concentrated there and you do your physics problems, assuming that's where the mass is, you'll get the same answer as if the mass is distributed the way it really is. And what this does, why we care, is because it makes the math easier. The center of mass means you have to do one calculation instead of integrating over a volume. And we far prefer the easy calculation. Now, if you've got a regularly shaped uniform object, a ball, a square, a long skinny stick, like a meter stick, the center of mass will be at the geometric center of your object. It'll be at the physical center. If the physical center happens to be empty, that's still where the center of mass is. An example of this would be the donut. Unless it's jelly-filled, a donut has a hole in the middle. It is empty, but the center of mass for that object would be in the middle of the hole. Suppose you have a volleyball. A volleyball is hollow in the middle. The center of mass for a volleyball would be in the middle of the ball, which of course is just empty space. So you can have the center of mass be at a place where there's actually no mass at all, but the math still works out. Yay for math. If we look at this wrench, if you throw it, if you toss it in the air, I don't suggest you do that, but if you did, it would begin to rotate as it goes through the air. But the interesting thing is that the path it would follow looks complicated, but the center of mass actually follows a nice parabolic arc, as if this whole wrench were just a little round ball being thrown up and it comes down. So the center of mass is a really handy concept. Now suppose you don't want to throw something and photograph it, or suppose it's not a regularly shaped object. How could you find the center of mass? Well, if it's an irregularly shaped object like this, you drop a plumb line. So suppose we support our object right here at the red circle. Maybe we drill a hole and hang it by a nail so it's free to swing. And then we drop a plumb line. So you tie a string to the nail with a weight on the end of the string and it comes straight down and we trace out the line. That's what this blue line is. If we took this same object and maybe secured it from this little place right here, we'd have to change it around. When we drop the plumb line, this blue line would be the plumb line. Where those two lines cross each other is the center of mass for this object. Center of mass comes in handy for all kinds of things. It's important in gymnastics. So in gymnastics, again, the gymnast contorts his body as he's moving through the air, but his center of mass is going to follow this arc as it moves along. If you look at a diver, it's the same sort of thing. So the diver comes up and makes their tuck and flips around and then hopefully gets a clean entry into the water. but the center of mass is going to follow this nice clean path. So we don't have to worry about where are the arms, what are the legs doing. For us, it's all about the math. Now there are two equations for center of mass, one for its location in the x direction, one for its location in the y direction. If we were doing it in three-dimensional space, we'd have one for the z direction. You do not need to memorize these equations. I will provide them for you, but I do want to describe what they're trying to say. So the x-coordinate for the center of mass is equal to, here is the little Greek letter, capital sigma. Capital sigma, and it is used to represent a summation where you do a little math for one item, then do a little math for a separate item and add them together. How many items? Well, that's what the indices on the summation notation tell you. I equals 1 means we start at item number 1. Having an n up above means we go to item number n. So this is a general form. We could, if we had 10 items, we would start at 1 and end at 10. If we had 2 items, we'd start at 1 and end at 2. You're not going to have to worry about writing it in summation notation. We're not going to work with so many items that it matters. We will just write it out. And then it's the distance from the origin to the mass multiplied by the value of the mass for each item, and then that sum is added together, and then you divide that by the sum of all the masses. So when you have only one term in a summation, it means take all the little parts and add them up. And you can see the only difference in the x and the y is in the x direction we had x for our distance, in the y we've got y. All the x's and y's are measured with respect to an origin. It is really important that you know where is the origin, where are we counting 0 at, because it moves around. Sometimes it's at the left end of the collection of items, sometimes it's in the middle, sometimes it's in the center of the first item. It just varies, so you want to be careful in your diagrams to know where is 0. So let's look at this first example. We want to find the center of mass for this collection of balls. We're going to measure from the center of the first ball. So 0 is right here in the middle of the first ball. We know the first ball has a diameter of 4, the second has a diameter of 3, the last one has a diameter of 1, and ball 1 and 2 are separated by a 1 meter gap, 2 and 3 by a 2 meter gap. And I like to group my masses and my distances together, because I think when I just list the distances all in a row, I sometimes match them up with the wrong masses. So they said mass 1 was 10, mass 2 was 20, mass 3 was 30. In class one time, somebody argued with me, how could the little one be the biggest mass? Well, maybe it's made out of lead, and maybe 2 is made out of wood, and maybe 1 is just a balloon full of air. I don't know. The physical size is not always indicative of the mass. So we know that mass 1 will make our table of knowns, finds, and formulas. We know that mass 1 is 10 kilograms. We know that x1 is 0. How do I know that? Because x1 is how far is the middle of the object from the origin. The origin is at the middle of the first ball. So the middle of the first ball is 0 from itself. All right. We're looking for the x-coordinate for the center of mass, and we have this big formula that I said I'd give you. All right, we need to know, we know the mass for number 2, it's 20 kilograms. But now we need to know how far is number 2 from the middle of number 1. So we're going to add it up from the middle of number 1 to the edge. From the middle of number 1 to the edge is how far? Well, it would be halfway of all the way across, so 2 meters. from the middle of object 1 to its edge would be 2 meters. So we know that's where this 2 meters comes from. From the edge of object 1 to the edge of object 2 is 1 meter. That's where this 1 meter comes from. From the edge of object 2 to its center would be halfway across. Well, 3 meters divided by 2 is 1.5. And that's where this 1.5 meters comes from. So 2 meters plus 1 meter plus 1.5 meters gives you 4.5 meters. Ball 3 is 30 kilograms. We know that it's 2 meters plus 1 meter plus, whoops, now we need to do it for object 3. So starting at the origin is right here at the middle of ball 1. It won't always be there. It might be on the left edge. It might be in the center of the picture. But for right now, it's at the middle of ball 1. So from the middle of ball 1 to the edge is 2 meters. So that's where this 2 meter comes from. From the edge of ball 1 to the edge of ball 2 is 1 meter. That's where the 1 meter comes from. All the way across ball 2 is 3 meters. All the way across ball 2 is 3 meters. That's where this 3 meter comes from. Ball 2 is 2 meters from ball 3. That's where the 2 comes from. And little ball 3 is only 1 meter across, so to the middle would be a half a meter. That's where the 0.5 meters comes from. So 2 plus 1 is 3, plus 3 is 6, plus 2 is 7, 8.5, 8.5 meters. Now that we have our masses and how far they are away from the center of ball 1, because that's where our origin is, we can do the math. So distance times mass for all 3 in the numerator, and then add them together, and the mass is in the denominator. So here's our equation in its general form. We've got 3 objects. You probably could get away with not writing these first 2 equations, but just doing the third one. Just do the third equation. So x1 times m1 plus x2 times m2 plus x3 times m3 divided by m1 plus m2 plus m3. So 0 times 10 kilograms plus 4.5 meters times 20 kilograms plus 8.5 meters times 30 kilograms divided by 10 kilograms plus 20 kilograms plus 30 kilograms. All right, so 0 times 10 is 0. 4.5 times 20 gives you 90 kilogram meters. I don't know why we don't write it meters, kilograms, but we never do. 8.5 meters times 30 kilograms is 255 kilogram meters. And 10 kilograms plus 20 kilograms plus 30 kilograms gives you 60 kilograms. So 0 plus 90 plus 255 gives you 345 kilogram meters. Divide it by 60 kilograms and you get 5.75 meters. 5.75 meters. And that would be measured from the middle of ball 1, not from the left edge, but from the middle of ball 1. The distance can be negative if our origin was at the center of the group. Some of our distances would have been negative distances, and who knows, let's see, where would 5.75 meters have put us in the picture? Okay, 4 meters. Here is 5 meters. To the middle would be 6.75. And that means we are to the left of the middle. So if our origin had been at the middle of ball 2, our center of mass would have had a negative value. All right. Oh, I lied. From the middle, so 5, what was it? I'm sorry. 5.75 meters. So from the center over would be 2, this would be 3, 4, and 5. 5.75 would put us right here, which would be to the right of the middle ball. Sorry about that. I forgot. You've got to remember, where are we measuring from? All right, enough of that. Let's move on. For your practice, you need to be able to do this. Sometimes we talk about center of gravity. Center of gravity and center of mass are usually in the same place, unless you're dealing with a really large object like a planet. It could be in a different locale. We're not going to worry about that distinction. For homework, instead of the balls, I want you to have 3 boxes, and you have their masses and their lengths, and I want to have 0 be at the left edge of the left box. So left edge of the left box, tell me where the center of mass is. You need to practice this. And there's some other practice problems in the study guide. So we need to move along to equilibrium. The sum of the forces acting on a body have to be 0 if you're in equilibrium. So what that tells me is that the sum of the forces in the x direction add up to 0, and the sum of the forces in the y direction add up to 0. That's the first condition for equilibrium. The second condition is that the torques acting on the object have to equal 0. Torque is the rotational equivalent of force. Torque is the rotational equivalent of force. So if you have a bicycle wheel and you're doing something with it and you come back, maybe you're attaching something to it and the wheel begins to rotate. It rotates because there's a torque on it. Torque is the rotational equivalent of force. It is, I'm gonna draw it for you because a lot of you don't do it very well. It is symbolized by the Greek letter lowercase tau. Lowercase tau. So it looks a lot like a little t, except, well, actually it looks like a capital T with some wavies on it, and it's only half size. So it comes up about halfway on the line. It would be a wavy top. And then normally, well, that's not what I wanted to do. I'm sorry. Let's try again. So a wavy top, and then we come straight down, or some people tilt it just a little at the tail. So wave at the top and then straight down. The top's not necessarily quite this long. I think I've told you before, it's hard for me to draw on the computer. And now this seems a little tall. But a wavy top and a line coming down. All right, I'm getting rid of that. I just have found most of you don't do your Greek letters very clearly. So wavy top, line coming down. No matter what my typeface looks like. So the sum of the torques acting in the body has to be 0. What that tells me is that the sum of the clockwise torques, CW stands for clockwise, will equal the sum of the counterclockwise torques. Torques vectors are normally measured with a compass direction like north, south, east, west, or right, left, up, down. A torque, because it's for rotational motion, is measured clockwise or counterclockwise. And interestingly enough, most books will tell you that clockwise torques are negative and counterclockwise torques are positive, because counterclockwise torques would pull you up, which is the positive direction, and clockwise torques pull you down, which is the negative direction. If you have trouble with clockwise and counterclockwise, ask me for help. Alrighty, so it is the rotational equivalent of force. Torque is measured in Newton meters, a Newton multiplied by a meter. And torque is equal to the force times the lever arm. So F is force, and R perpendicular is the lever arm. This symbol that looks like an upside down capital T means is perpendicular to. Some books use L's. When I had physics, we used a script L, but an L looks like the number 1 and it screws everybody up. So we have taken to using R's, but every book uses something a little different. So torque is force times lever arm. If we look at these diagrams, the red arrows are the applied forces. This is meant to be an overhead view of a door, this little thing sticking out on the right side of each drawing is the doorknob. And down here on the left side, that's the hinge. And again, we're standing above it, looking down on it. So the distance between the pivot point, which is the hinge for a door, and the applied force is drawn in right here. If you apply the force at 90 degrees to the door, then that distance of separation is the lever arm. So here we've got it in diagram A, it would be producing a clockwise torque. The door is going to swing up. In D, it's a counterclockwise torque. The door's coming down. In diagram B, where the arrow's a little shorter, so it's a little smaller force, there's less torque. In E, the arrow's at an angle. And so what that means is all of the force is not being used. What I would probably do is resolve the force into components. I would resolve the force into components. If we need to, we can do some examples with that. I might supply a little worksheet. And here we have the same forces we started out with, but we're closer to the pivot point, to the hinge. So again, less torque than the very first one. And the last one, we are, for some strange reason, trying to move the door by pulling on the end of the door jamb. That's not going to do it, as you well know, because the force and the lever arm have to be at 90 degrees to each other, and they're not. They're parallel in this one. So there's no torque in the last diagram. No torque. So what I would do, here we've got simplified drawings again, a short lever arm and a force, a much longer lever arm and the same force. So the middle drawing is a bigger torque than the first one. In the last diagram, the arrow for force was meant to be the same size as the other two. I know it's not, but it was meant to be. The perpendicular part is right here. And this little angle of theta was meant to be this little upper angle between the door and the force, which is the same thing as this lower inside angle on the triangle I have drawn. So the perpendicular component of the force is right here. And so this distance times that part of the force will give you its torque. And if the F in this case is the same as the F in the other two, this one, again, is smaller than the middle one for two reasons. We're closer to the edge, and if the vectors were supposed to be the same size, when you break it up into components, the hypotenuse is always the biggest leg. So F perpendicular is always going to be smaller than F, if F is at an angle. Okay, let's look at some statics problems. So we've said that the center of mass is, you can consider all the mass to be located. It's at the geometric center. I talked before about donuts and volleyballs. So here are just some pictorial examples of a circle and a triangle and a couple of boxes, and looks like a can shape. Let's look at a seesaw, which is the standard center of mass problem. So we have a kid who weighs 40 kilograms, which is a little heavy to be on a seesaw, and they sit 3 meters away from the pivot. Our seesaw is 5 meters long. That is over 15 feet. That is one long seesaw. We have child 2 over here on the right-hand side. They're 2 meters from the pivot. So this blue triangle is my pivot. So child 2 is going to be, what do we say, 2 meters from the pivot. 2 meters from the pivot. All right, got that. So we know that M1 is 40 kilograms. We know that child 2 sits 3 meters from the pivot. So I'm going to put that in my picture. And we know the total length is 5 meters. How do I know that? Well, they told us it was 5 meters long. I'm going to put that in my diagram. With seesaw problems and with torque problems in general, a picture is really important. So child 1 is 3 meters from the pivot. Child 2 is 2 meters from the pivot. We need to talk about the board itself. It is a 15 kilogram board. It is 5 meters long. The center of mass for the board, remember, for a uniform object, it would be at the middle. So for the board, it's going to be at the middle. The middle of a 5 meter board is the 2.5 meter mark. 2.5 meter mark. So if we come in 2 meters on the right-hand side, we've got to come in another 0.5 meter for the center of mass of just the board, which I'm calling SS4 seesaw. So the distance from the center of mass of just the empty board to the pivot point is 0.5 meter. Once you get your picture and the numbers organized, where again masses are matched with their lever arms, then we can start the problem. And we'll start it by saying, oh, this is supposed to be a subscript. I know it's like flying in space. I apologize for that. I should have fixed it. It should be that upside down T should be below the line. It's just acting crazy today. Oh, clockwise torques equal counterclockwise torques. If you don't know what is clockwise and what is counterclockwise, that's okay. So look at the pivot. Here's the blue triangle is the pivot. The child on the right, if they were the only one there, is going to force the seesaw down. And that's clockwise. So the child on the right of the pivot is the only thing pulling down on it. So the child on the right, which is child 2, is the clockwise torque. On the left side, child 1 would push down, but that makes the seesaw move in the counterclockwise direction. So torque 1 is the counterclockwise torque. Suppose nobody's on the seesaw. The fact that the board is not centered means that the board itself is going to flop down on the left-hand side. So the board itself will swing up. That's a counterclockwise torque. And if all of that has just confused you, all you have to do is look at the pivot and say everything on the right of the pivot goes on one side of the equal sign, everything on the left goes on the other side, as long as gravity is the only thing pulling on stuff. So this works, but not in cases when you are letting gravity pull down and something else pull up. If we're hooking it to a crane, you can't say everything on the right of the pivot goes one way and everything on the left goes the other. But we can with seesaws. So clockwise torques equal counterclockwise torques. Torque 2 equals torque 1 plus this torque for the seesaw. Torque is force times lever arm. Well, the force is the weight. So it's going to be mgr for child 2 and mgr for child 1 and mgr for the seesaw. We ought to be able to plug in. Mass 2 we do not know. G is 9.8 meters per second squared. And lever arm for child 2 is 2 meters. Equals. Why is my equal sign down here? Because there wasn't room on this line for the whole thing. So it dropped down. Equals 40 kilograms, that's the mass of child 1, times 9.8 meters per second squared, times the lever arm for child 1, which was 33 meters, plus mass of the empty board is 15 kilograms times 9.8 meters per second squared, times the 0.5 meter that the board itself is. The center of the board is a 0.5 meter away from the pivot point. And so now we do the math. The 40 times the 9.8 times the 3 gives you 1,176 kilogram meters squared per second squared. The 15 times the 9.8 times the 0.5 gives you 73.5 kilogram meters squared per second squared. Those two numbers are added together. We've got 9.8 times 2. That's the same as 19.6. To get rid of it on the left side, we have to divide. So everything gets divided by 19.6. If skipping that step is hard for you, put in the intermediate steps. And then we do the math. We take these two numbers, add them together, hit equal, and then divide by 19.6. So 63.75 kilograms. If you can't do that and get the right answer, you need to ask me for help. I will help you. But you have to, all I'll tell you to do is write out all the steps if you haven't done that. And then we'll look at where your mistake came from. So if you're making mistakes, write down more steps. All right, same seesaw. We're going to move the pivot to the middle of the board. Moving the pivot to the middle of the board. So what do we know? Our board is still 5 meters long. But now the center of mass for the seesaw is right here at the middle of the board, which is where the pivot is. So its R would be 0. The R for the seesaw is 0. It doesn't count. It has no lever arm. So we just have child 1 and child 2. Child 1 is going to be 40 kilograms. If the pivot is at the middle and child 1 sits on the left edge, child 1 sits on the left edge, then R1 is going to be 2.5 meters. We're going to let child 2 sit on the right end. That's where they were in the previous problem, right end. That means they're also 2.5 meters away from the pivot. So R2 is 2.5 meters. In our first example, they were at either end. It was the pivot that was wonky. In this example, they're still at either end, but we have slid that pivot over to the middle of the board. So we have all our numbers we can plug in. So here's where our math starts, right down here. Torque clockwise equal torque counterclockwise. We've only got 2 torques, child 1, child 2. The seesaw doesn't count because its R is 0. Its lever arm is 0, so its torque is 0. So child 1 and child 2. So it'll be torque is force times lever arm, which would be the weight. So M times G times R for 2 equals M times G times R for 1. We don't know mass 2, but we'd like to. So mass 2 times 9.8 meters per second squared times 2.5 meters equals 40 kilograms times 9.8 meters per second squared times 2.5 meters. You should notice that we have 2.5 and the 9.8 on the right, 2.5 and the 9.8 on the left. 40 kilograms on the right and M2 on the left. Somebody should have figured out by now that M2 is going to be 40 kilograms. But if you can't figure it out, you can do the math. So 40 times 9.8 times 2.5 is 980 kilogram meters squared per second squared. 2.5 times 9.8 is 24.5 meters squared per second squared. And when you do the math, you get 40 kilograms. So to balance the seesaw, if the pivot is at the middle and you're at either end, what you have on the right has to balance with the left. This is sort of the principle behind things like triple beam balances, and all kinds of balances use this torque principle. You hang something from one side and balance it on the other. All right. Let's change the masses up. We're going to make child mass 1 have a mass of 20 kilograms, and he's going to sit on the left end. The board is now 3 meters long, not 5, but oh, I lied. That's supposed to be 3. 3 meters long. So R1 is going to be, I bet my numbers are wrong then. R1 is not going to be 2.5, it's going to be 1.5. You see, I cut and pasted. So R1 is 1.5, not 2.5. What was I thinking? We want to know R2. We are not sure where that second child is going to sit, but we know they're going to weigh 40 kilograms. And we know that because the center of mass is at the middle of the board, and the middle of the board is where the pivot is, we have 0 lever arm for the seesaw. If the board is 3 meters long, child 1 is on the left edge, pivot's at the middle, child 1 is sitting 1.5 meters from the edge. And we don't know child 2. Well, the board is not 5 meters long. Thank you very much. It is 3 meters long. This is not 2.5. It is 1.5. There we go. I did this on the board in class when we met in real time. And so this virtual situation, I cut and paste too much. All right, so clockwise torques equal counterclockwise torques. Actually, child 2 is producing the clockwise torque. Child 1 is counterclockwise. Aha, I am going to have to fix my math. Which I can do. So 40 times 9.8 is 490 kilogram meters squared per, oh, I'm sorry, is 392 kilogram meters per second squared. Let's see what 20 times 9.8 times 1.5 gives me. 20 times 9.8 times 1.5 is 294. And that is my new numerator, 294 kilogram meters per second squared, and 294 divided by 392 is 0.75. And let's see if that makes sense. Child 1 only weighs 20 kilograms. Child 2 weighs twice as much. To keep it balanced, torque is force times lever arm, and the force is the weight. Child 2, if they sat on the end, because the distances would be the same, he would exert the larger torque. So to keep it balanced, because he weighs twice as much, he has to sit half as far away. He weighs twice as much, so he sits half as far away. You don't have to do it intuitively. The math really will work, especially if you plug in the right answers. All right. Let's look at a leg in traction. This is an example where you have all the forces on the same side of the pivot. All the forces on the same side of the pivot. And my diagram for a leg in traction is not really a very accurate one. They really don't normally do. Put your leg out straight, have a string come up, go over a pulley, go down over a pulley, and hang a weight off of it. The big blue box is the weight. It's going to be a 2 kilogram counterweight. But for purposes of illustration, we'll do it like this. So the hip is the pivot. I told you in the problem that the center of mass for your leg is at the 40 centimeter mark, which would be 0.4 meters. We want to know, where should we put this 2 kilogram weight so that your leg stays balanced, your leg is straight? Like I said, this is not a realistic traction device, but That's all right. So what do we know? We know that the mass of the leg is 10 kilograms and that the lever arm would be 0.4 meters. We know the mass of the counterweight is 2 kilograms, and we're looking for the lever arm for the counterweight. We know that torque is force times lever arm, and we know that clockwise torques equal counterclockwise torques. Well, before I said on the pivot, those on the right of the pivot go one way, on the left go another. Well, the pivot's right here, and the torque right here for the leg and the torque right here for the counterweight are both on the right. So we can't have 0 equal torque 1 plus torque 2. I guess we could, but one of the torques would end up being negative, which it technically is. But we're going to separate them. When you only have 2 torques and they're both on the same side of the pivot, one goes on the right and the other goes on the left. If you look at the leg, if you didn't have a weight on it, the leg would fall down. That's a clockwise torque. If you put the weight on it, the weight by itself pulls the leg up. That's a counterclockwise torque. It would pull the leg up counterclockwise. So the leg is the clockwise torque and the weight is the counterclockwise. But again, it doesn't matter as long as you've got one on one side of the equal and one on the other, we're good. So mgr for the leg equals mgr for the weight. The mass of the leg was 10 kilograms, 9.8 meters per second squared, and r was 0.4 meters. For the weight, 2 kilograms times 9.8 meters per second squared times r. So 39.2 is going to equal 19.6 times r. Divide both sides by 19.6 to get that out of the way. And we find that the distance for the counterweight has to be 2 meters, which means the leg from the hip to where you hook that counterweight has to be over 6 feet. Actually, it's over 6.5 feet. A meter is more than 39 inches. So that is one long leg. You are a super tall person if you have legs over 6 feet long. I told you it was not realistic. All right, stop the video.